Okay, so we are going to continue our related rates examples with example 5. And example 5 and example 6 are just somewhat a little off basic, okay? So, especially example 5. You have at 1 p.m. a ship A that is 25 miles due south of ship B. Ship A is sailing west at 16 miles an hour and ship B is sailing south at 20 miles an hour. Find the rate at which the distance between the ships is changing at 1:30. So, drawing this, you have to think, okay, at 1 o'clock, ship A is due south of ship B. Okay, so at 1 o'clock, ship A due south of ship B, and that distance between them is 25 miles. Now, they're going to be moving. Ship A is sailing west, so it is going in this direction. Ship B is sailing south, so it is going in this direction. And we want to find the rate at which they're changing, or the distance between them is changing at 1:30. So at 1:30, let's say that these are their new positions. A is right here and B is right here. The distance between them is as the crow flies, so the shortest distance is a straight line. Okay, so B has traveled a distance of y, and A has traveled a distance of x. Obviously, this does not look like geometry shapes that you're used to, so let's close this off and make this a right triangle down here. Now, what's important about this is that B has traveled this particular distance right here. Not the entire thing necessarily, maybe, maybe not, but most of the time not, because they usually give us a triangle to work with. What we need to know is that is y, and the whole thing adds up to 25. So I can call this little piece of the triangle that I have dotted 25 minus y, because I need to represent it with those variables. And this is the difference between what we did in the latter problem and what we're doing right now. So I'm going to make a list, because every time we have a triangle, we have 3 sides. And we always talk about the lengths of those 3 sides and the rates that those 3 sides are changing. So the triangle ones, I always just start out by setting up everything so I can just figure out what my given information is. So I always have the lengths and the rates for each side. So the first thing is the rates they actually give us. Ship A is sailing west at 16 miles an hour. So that's the rate that A is sailing, and the A is sailing along the x direction. So I'm going to call that 16 miles per hour for dx dt. And then ship B is sailing south along that y right there. So this is dy dt. Is 20 miles per hour. And it says find the rate at which the distance is changing, so finding the distance rate, that's what we're trying to do. That's where my question mark is. Now, all of that is what they gave us. Now we have to come up with what we just know, or what we can figure out. 30 minutes has passed. Ship A started at 1 p.m. It's now 1:30. So you can figure out how far it went. It was sailing at 16 miles an hour, and it's only traveled for half an hour, so ship A has traveled 8 miles. Ship B was sailing at 20 miles an hour, and again, it's traveled for half an hour, so ship B has traveled 10 miles along that y. So that x distance is 8, and that y distance is 10. Now, we have to kind of come over and do a little bit of scratch work. So, on the triangle that we know that x is 8. If the y is 10, 25 minus y would be 15. So this side is 15. And I need to do the Pythagorean theorem to figure out what that d is. So I'm going to have d squared equals 8 squared plus 15 squared. And when I solve that, I get d to be 17. So that's my scratch work. I can figure out that d is 17 miles at that particular point in time. Now I'm ready to do my equation, and again I want to think about this triangle right here, and I'm doing Pythagorean theorem with that. So x squared plus 25 minus y squared equals d squared. That is my Pythagorean theorem for the unknown triangle here that's changing. Now I do the derivative. So I say chain rule 2x, derivative of x is dx dt, or if you're using primes, you can use prime there. Then again I've got a chain rule here, so 2 times 25 minus y. The derivative of negative y would be a negative dy dt. And the 2d is also a chain rule, so 2d and dd dt. And again, because it's Pythagorean theorem, every single time you get those 2's in front, and I just get rid of them just to make my math not have as big of numbers. And then I'm going to plug in. So I'm going to plug in 8 for the x, 16 for the dx dt, 25 minus 10, and then negative 20. And then d is 17, and I'm finding dd dt. And it's nice, this whole side is numbers. You can just figure out what that is by typing in your calculator or doing the math in your head really quick. You get negative 172. And then you just divide. So you get negative 10.117 miles per hour. And again, I know that's my units because my distance is measured in miles and my time is measured in hours in this case. I went with a decimal on this version. You need to get used to rounding to 3 decimal places. It needs to be correct to 3 decimal places. Okay, now example number 6 is probably the most challenging one we're going to do in these examples. And I'm showing you this because this is something that once in a while comes up, but it's not really considered one of the basic problems. This one has to do with angles. So let's read this. It says a revolving beacon in a lighthouse makes 1 revolution every 15 seconds. The beacon is 200 feet from the nearest point P on a straight shoreline. Find the rate at which the ray from the light moves along the shore at a point 400 feet from P. So this is one of those that if you need to reread it because there's a lot going on right here. So I'm going to say here is my shore and here is my beacon, so I'm going to name it B. And it says that the nearest point P on the shoreline. So the nearest point is obviously straight over. And so I'm going to put P over here on the shore straight from B. And because I'm trying to figure out how this works with geometry, I'm going to put a line between those at the moment. And then we're talking about this question that asks the rate when the light is 400 feet from P, but it's on the shore. So along the shore at a point 400 feet from P. So I'm just going to go this way. You could have gone up, but because of the way I drew my picture, I'm going to put this point down here. Okay, so this is the point they're talking about. And again, if you look, we're kind of making a triangle. So I'm going to make a triangle out of it. I'm going to call my horizontal side X and my vertical side Y. And I know both of those values. The distance from the beacon to point P is 200. And the distance from point P and to that other point that they're talking about is 400. So I know those two values, but again, we don't ever plug in till the end, so I'm going to go ahead and call them X's and Y's in my picture. Now, what makes this funky is that they're saying this happens 1 revolution every 15 seconds. What is that? Okay, revolution, we're talking about a circle, making a circle. And so this beam is making a circle as it travels around. And so we're actually talking about angles. So I'm going to put a little theta right here. And so I'm going to need to know something about theta. And with these three things, obviously, like we did with the Pythagorean theorem, we're going to have some rates. So dx dt, dy dt, and d theta dt. Well, x is not changing. That's the distance between the beacon and point P, so its rate of change is 0. So that one's easy. And dy dt is actually what we're trying to find, because we're trying to find the rate that the ray of light is moving along the shore. And so that is how y is changing. And so that is our question mark. Now, the d theta dt is actually coming from that one revolution every 15 seconds. So if you think about, I'm going to come do scratch work here, d theta dt, well, the light is making one whole circle, and we're in radians, so one whole circle in radians is 2 pi. So it goes through 2 pi as an angle every 15 seconds. So 2 pi radians every second. Okay, so that's me figuring that rate out. So that is 2 pi over 15 radians per second over here. And then the other thing I'm going to do with my scratch work is figure out what theta is. So if I plug those values in that we know, the 200 and the 400, I can figure out what theta is, because that's an opposite and adjacent side, so that would be tangent. Theta is 400 over 200. To get that theta, I can do an inverse tangent. So theta equals tangent inverse of 400 over 200. Again, you want to make sure your calculator's in radians, since we're doing this in radians over here. And you should get a decimal, 1.10714 radians. I'm going to keep all those because I need to be correct to 3 decimal places at the end, so I need to keep some more while I'm actually doing the work. Okay, so now we have everything that we're given, and we go back to our picture. This is not a Pythagorean theorem problem because we don't know anything about this third side. We do know about this angle and these two sides, and so the relationship that you have to get from that to get an equation is the tangent relationship we just used. So tangent theta is y over x. That means that I'm going to be taking the derivative of both sides here. I need to know my trig rules, and I need to know my quotient rule. So I'm going to start on the left. The derivative of tangent is secant squared. And I'm doing a chain rule, so times d theta dt. And then on the right side, I'm doing a quotient rule, so the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And so then I have everything to plug in except that dy dt. So I have secant squared of 1.10714 times d theta dt, which was 2 pi over 15. And then over here on the right, I have 200 times dy dt minus 400 times 0 over 200 squared. So I have everything plugged in now. Now, if you have this in your calculator and this happens to be the last thing that you typed in to get this 1.107, you can just do 1 over the cosine of that squared. and use second answer so it pulls the entire decimal, and that will be the best way to get the most correct answer. But you don't have a secant button, so you have to do the 1 over cosine and make sure it's squared. And then you multiply by the 2 pi over 15. Now, what's nice is if you use that second answer and get that whole decimal and do it correctly, that actually ends up to be 5. So you have 5 times 2 pi over 15 on that side. Now, over here on this side, obviously 400 times 0 is 0. You end up with 200 dy dt over 200 squared. And you can reduce that to 1 over 200 dy dt. And I'm out of room, so I'm going to come over here. This 5 times 2 pi over 15 will become 2 pi over 3. And I just need to multiply both sides by 200 to get that dy dt. So I have 400 pi over 3, or whatever that decimal is. And then I'm in feet per second is my dy dt. So I went from here up to here. Okay. So hopefully you understood what we did and realized that occasionally you do get a trig relationship, not just some kind of volume area type formula. So that can happen. That concludes this lesson on related rates.